Well, good morning, everybody, and welcome to our Green Hydrogen Day today at Engineering Tomorrow. We're so excited that you are here live to participate in the event. Today, we have the amazing Dr. Eric Einstedt, who's going to be leading the lab, and this is his lab. So we're excited to have him present it, and we're going to get rolling. Eric, take it away.
All right, thanks, Monica. And hi to everybody. It's really exciting to have you here. And really, as Monica said, this is a brand new lab, so we're very excited to see how it goes and how successful you are. And then at the end of the day here, you're also going to have a really great talk by our special speaker, Dr. Vijay Mittar, and he's going to talk a little bit about. He's a chemical engineer and has had a lot of different experiences, is working in the green hydrogen field. And he's going to tell you a little bit about what he has done. And he has a ton of patents. So if you're interested in learning about inventions and innovation and stuff, he is the guy to talk to. So we can look forward to that. But let's get started on the lab itself. So let me, I'm stuck here. I only have my laptop today, so it might be a little bit clunky, but I'm going to try to share my screen successfully. And you let me know if all's good here.
Good.
Can everybody see that? Okay, great. So we're going to talk about green hydrogen. So green hydrogen, why is this important? And we're going to get to that because green hydrogen is an element or a possible solution, not a complete solution, but it's at least one of the things that can be that can play a role in essentially decarbonization. So we'll talk about that in a little bit here, but let's move forward here. And as hopefully you know, with our Engineering Tomorrow labs, they're all developed by engineers. So I worked on this together with Grace and Allie. I think you're probably going to meet some more of our college engineers during the day today. We have some other helpers too. So let's get to the question: what is decarbonization? So essentially, it's something that the world is trying to do right now. It's essentially the reduction or elimination of CO2 or carbon dioxide or other gases that kind of behave like CO2. And the whole concept here is these gases, which are also called greenhouse gases or GHGs, basically when they're in the atmosphere, they make the Earth behave like a greenhouse. Like, if you know what a greenhouse is, it's a glass house where the sun's rays can come in and the sun's rays heat up the house, but you don't have a lot of loss of energy because the warmth that's in the house very slowly dissipates through conduction and convection, and so you're heating with radiation, but you're not losing so much. So you kind of get a warm place, and that's generally what's happening is that the atmosphere behaves like the glass, and our Earth temperatures are starting to go up. So, I know that there's some people think, this doesn't really matter. This isn't real. Well, let's look at something that's very specific. Let's talk about some of the data. And instead of talking about temperatures, let's talk about just CO2 levels in the atmosphere. So what I'm going to do is show you a number of plots and graphs of data in the next several slides to try to paint a picture for you using facts of kind of where we are today. So we'll start off with, and this is basically how engineers work. I mean, engineers are using data to design things and to understand things and to create things and to tell stories. So, these plots are meant to be ways where you can translate data and information into stories that people can understand. So if you look at the plot on the left, this is a plot over 400,000 years of the amount of carbon dioxide in the atmosphere. And how do they know this? Well, they can go in and they can take air samples, underneath the polar caps and the glaciers, and there are ways that they can get samples and analyze the CO2 levels. And as you can see over these many hundred thousands of years, there are cycles. There are climate cycles where you have an increase in CO2 and then it goes down and then up and down. But I want to show you right here at the very right-hand side of this graph, it's really compressed. And what's happening is that with the CO2 levels we're seeing today are just spiking. And they're extremely high. So if you look at the plot on the right, This is kind of a blown up version of just that last couple to, what is it, about 200 or 300 years. And the pink line is, again, the data that's plotted on the left-hand side there is the CO2 level. So you can see it was back in the late 1700s, it was somewhere around 280 parts per million. And then it's now gone up to over 400. So that's the curve, the pink curve that's you can read on the left side of the curve of the graph. If you look at the other curve, which is, I guess, dark blue or black, you read that on the right-hand side. That is a measure or a calculation of the amount of CO2 emissions from industry on Earth over the years. And as you can see, again, back in the late 1700s, early 1800s, there wasn't much emission. There people would burn fires to stay warm, but it wasn't a big driver. And then you get to the mid to late 1800s, and you start having the Industrial Revolution. And now people are burning coal on a very large scale. They're mining coal, burning coal, for steam engines, for factories, things like that. And then over time, we've basically started to do and use more and more, industrialized processes. And you can see that the amount of emissions is going up. And it's really kind of following the increase in CO2 levels. So this is one of the reasons why people essentially say, this has got to be related. So what's happening is that man is actually impacting CO2 levels. And the impact of these greenhouse gases and CO2 levels, again, can't say absolute for sure, but all the evidence points to that this is probably a big factor that's driving change in our climate. And everybody knows that every year hurricanes get more severe, the weather gets more extreme, heat waves are longer and hotter. Even cold spells can be very, very, severe, and more severe than they have been in the past. And these things, glaciers are melting at rates that, have never been seen before, certainly in humankind. So the feeling is that these severe weather events, rising sea levels, have to be driven somehow by the climate change, which is probably driven by these greenhouse gases. So that's the premise, and that's kind of what we have to assume is happening. So next question is, where do these CO2 and greenhouse gases come from? So this is a bar chart. In fact, what sometimes this type of a chart is called a Pareto chart, because it lists in order of magnitude the input, of each of these categories. And as you can see, the biggest emitters of greenhouse gases today is China, and that's driven primarily because China over the last 20, 30 years has been industrializing very, very, very aggressively. They've brought millions and millions of people out of poverty and to middle class. These middle class consuming these days is actually in using coal. So coal emissions, coal plants to make electricity is what's driving a lot of that. So that's one of the big drivers of why China is a big emitter of greenhouse gases. Now, I just want to talk about some of these greenhouse gases. You see the chart here. It's called the Kyoto gases. These are the carbon dioxide equivalents impact of these various gases. So if we say carbon dioxide has an impact of 1 for greenhouse impact, you can see methane is actually 25 times as bad. So a pound of methane is 25 times more impactful than a pound of carbon dioxide. You get to the next one, nitrous oxide is almost 300 times as impactful as CO2. And you get down towards the bottom here, you'll see all these fluoride-based gases, which are thousands of times more impactful. So these are all gases that they're also trying to monitor and reduce the impact of, or reduce the emissions of. So let's look at a different way of analyzing where the CO2 comes from. So in the this is a pie chart, and it kind of breaks down the total pie, 100% pie. into the various industries, or basically industries of where this the greenhouse gases are coming from. So you can see that electricity, so generating electricity from coal, is a big part of it. Electricity is a little over a quarter of our total source. So coal burning is a major factor, a major piece of that. Natural gas is also part of it. Oil is not used quite as much in electricity generation. If you look at the transport, start marking. Can you see me actually, or sorry? Oh, did I stop my video? There we go. Transportation is a big part of it, 16%. And transportation, that obviously includes cars, ships, and airplanes. So this is another area where there's a lot of greenhouse gas emissions coming from that industry. You'll see that agriculture actually has a real play here. I mean, the livestock and crops. I mean, if you're not efficient in your crop fertilization, that can cause excess greenhouse gases to come out. So these are all, basically causes of greenhouse gas emissions. So the question is, what can we do about it? So one of the things we can do, we can get at the electricity pie slice there by replacing some of our fossil fuels with renewable sources, so wind and solar. For transportation, there's a lot of people doing electric vehicles. You may have done our electric vehicle lab, using electricity, presumably from renewable sources, to charge batteries, and then those batteries can be used. And then there's also things like sustainable fuels, where you can create fuels that are much friendlier, I guess, greenhouse gas friendly in burning. But one of the issues we have, and basically all these things, all the things that we're trying to do, all are fit into the category of the energy transition. So the energy transition is really a transition that the world is trying to go through, where they get and start driving lower carbon intensity industries. So moving transportation more to batteries and renewable fuels, sustainable fuels, moving electricity more to renewable sources, so wind and solar and hydro. Basically, there's a lot of investment that's required to go into this energy transition. One of the challenges, and you're going to see it on the next page, is this industry category. It's the biggest of the categories, but there's no one great simple solution to driving down industrial greenhouse gases. So I've showed you some of the reasons where we're getting a lot of greenhouse gases out of the industries, various industries, and it really varies a lot. So in the iron and steel industry, they use these very, very high temperature blast furnaces, which have to be heated with energy. So again, it's either coal or natural gas that's often used to heat these furnaces. Again, that's creating greenhouse gases. Also, the reduction of iron ore. A lot of the chemical processes require hydrogen. So in oil and gas production, when you're producing oil and gas, especially oil, there's extra natural gas that comes out, methane. So again, you remember the methane is also greenhouse gas. So that's often flared, burned, or sometimes it just gets released accidentally because they're not capturing it. That happens in coal mining. If you have a big bed of coal, there's actually methane in that coal, and that's called fugitive coal bed methane, and that can release into the atmosphere. Cement production, there's calcination that actually causes greenhouse gases to be released. So these are all issues. These are all things that are different reasons. In the chemical industry, making methanol and ammonia, hydrogen is used. So what you might see is throughout a number of these things, hydrogen kind of keeps showing up as a key element here. And let me explain why hydrogen is an interesting element or an interesting compound here for this whole question. Basically, it's because traditionally hydrogen is produced in a method that actually generates CO2. So let's look at how that happens. So today, hydrogen is mostly produced with methane as a starting material. So what they do is they do something called a steam reforming and water gas shift reaction, where they take methane, which obviously comes from the ground typically, and they react it with water to make a CO and a hydrogen. And then that CO is continues to react with water, and you get CO2 and hydrogen. So the net reaction is that methane and water turns into CO2 and hydrogen. So that's why CO2 is a byproduct of the production of hydrogen. Now, there are different ways of making hydrogen. In this diagram here, you can see what we call the gray hydrogen. And I think EJ might explain some of this also when he talks at the end of the day here. Here's you have natural gas coming in, you have water, steam, you create CO2 and hydrogen. And in gray hydrogen, the CO2 is just released to the atmosphere. Fine. So one option you could do is take that CO2 and actually capture it so that it doesn't get released to the atmosphere. That type of hydrogen is what they call blue hydrogen. So blue hydrogen is lower intensity than gray hydrogen, obviously. So these are all starting from methane. So that's by definition not great, because there can also be some methane losses in the whole process. So one other option is to do something that really doesn't start with methane, produce hydrogen in a different way, and that is through a process called electrolysis. And the way electrolysis works is that if you have water obviously has hydrogen and oxygen in it. What you can do is use electricity to break that water into hydrogen and oxygen gases. And that's the electrolysis process. And so you can see it in the little diagram here, and this is what you're going to be doing today. You're going to be building a mini electrolysis cell, and you're going to create hydrogen. And what we want you to do is try to capture that hydrogen. So this is what it will look like on a very small scale. On a large scale, so here's the electrolysis process. You can see that's what's called green hydrogen. So you have clean electricity. If electricity was generated through renewable sources, then you have clean electricity, you have clean water, and you produce hydrogen. And you can produce this hydrogen without any carbon emissions. Now, to do this properly, this needs to be done on a large scale. It's not going to be a little electrolysis cell. It's going to look like this diagram here of a very large hydrogen production, green hydrogen production facility. So what the bottom line is that for every pound of hydrogen you make or you produce, you won't produce any CO2, which is the goal here. So all those places where hydrogen is used that I showed you on this previous page, now you have taken out part of that footprint. Part of that carbon footprint is now reduced dramatically by using green hydrogen. So this is then the concept. Green hydrogen kind of economy looks a little something like this. What you would do then is you would start up here with renewable energy, wind, solar, geothermal, other types of renewable energy. That produces electricity on the grid. That electricity on the grid can be used to charge your electric vehicle. It can be used to run the fans and run heat pumps in your house, which are also not burning of fossil fuels in order to heat your house. They can use for, electricity can be used for lighting and everything else, obviously. Part of that electricity, that green electricity, can then be used in an electrolysis process to produce green hydrogen, which the chemical industry could use, which they can use to produce fertilizers and chemicals, which other chemical industries can use to produce these sustainable aviation fuels, which can be used to run aircraft and ships and trucks and things like that. So this is the idea, and it's a great idea. And really at the core of it all is green hydrogen. But there's one problem with this idea. That is that if this will never work if it's not economical. So in order for this to be kind of a future solution or to some of our greenhouse gas emissions, we need to have engineers, we need to have technicians, we need to have operators, we need to have people who are trained up to figure out ways of making these processes economical and how to make them efficient. And probably at the same time, we need some incentives from, say, governments to help build this industry. And that is actually happening. There are a lot of incentives in the US for, obviously, for renewable energy, and also for green hydrogen, to try to create more of the technology, more of the scale to make this type of picture of the use of green hydrogen a reality. Okay, so let's get to what you're going to work on today. And I hope you find this lab fun. I think it's actually quite cool. What you should have is just a couple of very small, simple things that you could find around the house, really. You're going to be you should have a plastic bottle so that have something to put water in. This is water, obviously. I have my little plastic bottle, which I cut in half for a little pool there. You're going to use a clear straw to capture your hydrogen. And then you're going to use a battery. I believe we just provided the battery, not the solar cell for this. So just to pretend this is a battery that was charged with renewable energy, you're going to use some jumper wires to make your circuit. See if you can see it there. And then you're going to use essentially just two pencils. Two pencils are going to be your electrodes. So the electrodes of your cell. It doesn't always get in focus. Well, you can see it there. So this is what you're going to use to make an electrochemical cell. And what we want you to do is create hydrogen and capture that hydrogen. So this is how it's going to work. You're going to hook up you're going to make an electrochemical cell. You're going to fill your little cup with water. You're going to hook up a circuit so that the negative side of the battery goes to one pencil. And that pencil is the one that's going to be creating the hydrogen. That's going to be the hydrogen side, because what you're actually doing is taking the water and splitting it apart using electricity. The positive terminal is going to be hooked up to the other electrode. That's going to produce oxygen as long as you have clean water here. And what we want you to do is then create a little tool or a little vessel to capture the hydrogen, but I'll show you that in just a second. For those of you who are in chemistry or in chemistry class, this is essentially, or have taken it or like chemistry, this is essentially the process. This is the chemical reactions that are going to be occurring. One of them at the anode, one of them at the cathode. Again, the negative terminal side is going to be the hydrogen. You're going to be making, I guess, twice the volume of hydrogen as you would oxygen, because obviously there's two H's and only one O. So let's go to the next page. So one of the keys to this is to be successful at this is to make sure that you've taken your straw, your clear straw, which is how you're going to capture this hydrogen, and really sealed off one end. So what I've done in my case here is I've taken my straw, I put some glue inside the straw at the end, and I pinched it off and I folded it over. Now, it's really important that this is totally sealed. And the reason it's important is because hydrogen, first of all, if it's not sealed, you're going to have air leakage into this before you actually start to generate hydrogen. And that air leakage is going to be a problem. The second thing is hydrogen escapes very easily. It's a really small molecule, so you want to make sure it's really, really sealed up. So what I'm showing you here on the well, actually, let me stop sharing for a second so I can talk you through this. Can you see me?
Yes.
Here. Okay. So what you have is, again, here's your little cup with water in it. You know what I'm going to do? I'm going to get rid of my blur, so maybe it'll be easier to see. Okay, so you have your cup and you're going to have water in this. Here's my little straw. And what I've done is I said I've sealed off the end to be hopefully pretty much airtight, literally airtight. So what I'm going to do then is I'm going to take and turn the straw upside down. I'm going to fill this with water, and I'm going to put my finger over it. And then this cup should also have water in it, not all the way to the very top, but kind of maybe 3/4 up or 2/3 up. Once I've got this straw with water in it, I'm going to put my finger over it, and I'm going to turn it upside down, and I'm going to put it in the water in my cup. If I've done this right, and the straw is sealed off properly, that water will stay in that straw, and it will not drain out because of the back pressure. So if that water stays in the straw, you are in good shape. So you might want to let it sit there for a few minutes. Make sure it doesn't start to drain out. If it's draining out, that means that air is leaking into the top of the straw. So that's what you want to make sure. And then if that's the case, try to get some more glue in there. Try to seal it off some more. Try to really make sure that water stays in there. Then what you're going to do is you're going to take your electrodes, the pencils. I've actually taped them together, but you don't have to do that. And you're going to put the electrodes in the water, and you're going to place what's going to be your negative electrode somewhere underneath this straw. Then what you do is you hook up your electrical circuit with your electrical wiring and your battery. And once that's all hooked up, if you look at the end, the little graphite at the end of your pencils in the water, you should start to see little tiny bubbles forming, and they're going to be really, really small bubbles. You're not going to be like generating a ton of gas here. It's going to be very slow. But what I want you to do is try to figure out how to position this, how to design this in a way that when those bubbles actually release from the pencil, they go up in the straw. And over time, that gas is going to go up in the straw, and it's going to push the water out of it. And you should then start to see kind of an ever increasing amount of clear space at the top of your straw. And that clear space will be filled with hydrogen. That's the hydrogen that you've generated. Let's go back here. Screen, no, this one. All right, are we back here? That works. So this is what it should look like. This is what it should look like. As the gas is forming on your electrodes, you're pushing this water back down, and this is now hydrogen. And it's a very small amount of hydrogen. People ask, oh, this is hydrogen, it's dangerous, is it going to explode? So first of all, you're making a very small amount, so there's really no danger. I know that some of the questions that were posed earlier, there was a question about, is this really hydrogen? Yes, it is. Isn't hydrogen dangerous? Couldn't it explode? And on an industrial scale, on a large scale, on the use of hydrogen, all gases that are used, whether it's hydrogen or methane or natural gas, they all have a risk of some, of things going bad. I mean, there are dangers in natural gas that people use in their homes. Sometimes you see tragic, news items where a house exploded because there was a natural gas leak and it ignited. Natural gas also has the issue of when it burns, it could form CO, carbon monoxide, which is also a dangerous gas, and it's a clear gas, you can't see it, and it causes people to get sick and sometimes die. So every gas, every utility gas, if you will, has risks. Hydrogen has risks too, but there's a range of percent hydrogen in a room where it can hit its potential explosion limit, and you need to obviously stay away from that level. You can look it up if you'd like. There's an explosion range. But one of the benefits of hydrogen is that, as I mentioned, it's such a small molecule, it escapes so readily, it's hard to build up a lot of hydrogen in the room. The company I work for is called Global Infrastructure Partners, and we work with a lot of infrastructure around the world. And one of the projects in one of our companies is actually a green hydrogen project in Scotland. And what the project is, they're using a wind turbine to create electricity. They're building an electrolyzer to make hydrogen gas, and then they're piping this hydrogen gas to local homes, and the local homes have special appliances for their stovetops and for their furnaces that can burn hydrogen gas. So this is a test project just to see how this can work. But it's some of the things that we have to be concerned about or be aware of is, make sure there's enough ventilation, make sure that the piping is sealed. I mean, there's a lot of safety that goes into it. But that's true for hydrogen as well as for other natural gases that are used, whether it's propane or methane. So hydrogen can be dangerous, but it won't be dangerous for you on the scale that you're producing. So if you get a chance, if you have some salt, which I'm not sure if we give it to you, that maybe after you've produced your pure hydrogen in the first clean water, you can add some salt to your solution. And then what you'll produce is not only hydrogen, but you'll also produce chlorine gas. And you should be able to smell that if you get that far. And it'll probably smell like a swimming pool, because chlorine gas is used for cleaning and for disinfecting swimming pools. So that's what you're going to be working on today. Before you get started, I just want to talk a few more things about the kind of opportunities in the energy transition and in hydrogen economy in general. The energy transition, as I mentioned, really is in need of the next generation of employees, and that's what you guys all are. You are the young people that are going to be soon starting careers or continuing their education and eventually getting into careers. And although we are engineering tomorrow, and we really want to inspire you around being engineers, which typically means going to a 4-year college. We would love to see you do that. There are other ways to be an engineer, maybe not a degreed engineer, but there are other engineering types of jobs where you're basically you're an operator or you're a technician, where you still have to learn and understand these things. And these are skills you can learn in other areas, in 2-year colleges, in tech schools, technical schools, and also, in order for this energy transition to happen, we need people who can build plants and who can solve problems and who can manage electrical systems and plumbing systems and water systems. So there's also a real need for more than just engineers, all kinds of trade and craft labor. So there's a lot of opportunities out there. So I think if you find any of this just interesting, if you like working with your hands, if you find it really cool that you're generating hydrogen and you're collecting it and you have ideas of how to do it better and how to do it faster, I mean, maybe you should think about, you're then probably naturally a problem solver and interested in technical skills, and there are many ways that you can do that and apply those interests and have great careers. So that's all I have for now. Let's give it back to Monica, and I think she'll give you directions for the rest of the day, but you should now understand enough and have the tools you need to get started on making some green hydrogen.
Well, before we get to any more instructions, we want to give Eric a round of applause for a fantastic introduction for our day today. I hope that everybody is excited to pull out their kits and get rolling with their designs.